Today, I'm excited to share with you my research progress focused on leveraging the large language model with domain adaptation. The goal is to enhance community directory through deep learning text summarization from machine-readable cataloging standard description nodes, also known as MARC nodes. Before getting into the method and results, let's quickly touch on the research background. Our goal is to create an LP-based system that generates informative summary from South Australian Community Directory while complying with the MARC notes from the Library of Congress. These are the research questions we formulated earlier and the corresponding proposed solution. Moving on to the data and task, the dataset composition revealed a high ratio of unlabeled data with limited ground truth, also their organization in South Australia. The main task is to perform summarization with domain adoption. Specifically, we aim to leverage the unlabeled data by utilizing extension embedding and fine-tuning to enhance the performance of our summarization progress. Now, let's take a closer look at the method we have used. Our journey begins with experts, short for extend BERT pre-trained model. It starts with the pre-training of BERT to transform it into experts. Once pre-training is complete, we move on to fine-tuning expert into expert sum for the downstream task of task summarization. To start with, we concentrate on the pre-training of expert, where we infuse the original BERT with domain-specific vocabulary. The approach unfolds in two components. On the left, there are extension vocabulary and embedding layer. This enables more meaningful tokenization of the input text. On the right-hand side, the graph shows how we enhance each transformer layer of the original BERT, often refers to off-the-shelf, by adding an extension model to its side. And then we use weighted combination mechanism that allows two to cooperate. This quickly show how the extension vocabulary is formed. Without going into details, we have expert word embedding, which are derived by combining the original word embedding with the additional word embedding, denoted as word embedding ADD. In short, extension models are composed by the following architecture. Our process involves vocabulary adoption through transfer learning, with BERT based on case at our starting point. We incorporate unlabeled custom datasets into the pre-training process. The result is an adopted model with specialized vocabularies. In experiment 1, we investigate the impact of data representation. We compare open field columns to a combined dataset that include both open field and closed field columns. This experiment aims to investigate how the choice of data representation affects the performance and outcome of summarization. In experiment 2, we are exploring different module size, ranging from S1 to S5. Here, S5 represents a full-size transformer module. S1 to S4, on the other hand, are partial modules, each with a unique ratio compared to a full-size module. The table here provides insight into corresponding hidden size, the number of feed-forward layers, the intermediate size, and how these parameters relate to the original BERT model. This experiment helps us understand the impact of module size on our module's performance and capability. In the case of Expert, it employs a dual configuration setup as illustrated here. We pre-train the model by initializing it with predefined weights. It is important to note that the off-the-shelf part remains completely fixed throughout the process. However, we make updates to the extension module and weighting block during the training phase. The table shows different hyperparameter setups for experiment 1 and 2. When we experiment the pre-training foundation loss, the best outcomes are achieved with open field copies with specified patch size, learning rate, and epoch. We will carry on this set of modules to the downstream tasks, particularly focused on task summarization. Moving on to expert sum. To translate expert to expert sum, it involves a critical adjustment to the segment embedding architecture. This adoption is essential for ensuring expert sum can effectively generate test summaries. In XPRSUM, we still rely on the concept of token type embeddings to differentiate between the input text and the summary, just as we did in Expert. In addition to that, we now input data with symbols that represent the beginning and the ending of sentence. To perform text summarization, it is essential to distinguish multiple sentences within the source text. These additional steps enhance the model's comprehension of sentence structure. Building upon the foundation of experts, XpertSum incorporate additional components for position embeddings. These embeddings are initially set randomly and are fine-tuned alongside other encoder parameters, as demonstrated here. In experiment 3, it focused on comparing XpertSum with and without extension embeddings. In our experimental setup, we have models of XpertSum with different extension embeddings from S1 to S5, and the baseline summarization model without the extension embeddings. This experiment will show impacts of extension embeddings on our XpertSum model performance compared to baseline BERT model. We are working with approximately 600 pairs of article and their corresponding ground truth summaries. To prepare this data, our initial steps include tokenization and sentence splitting for further analysis and processing. These are the hyperparameters set up for the experiment. When it comes to fine-tuning, it's important to highlight that we have achieved the best result with time-to loss configuration labeled as S2. This particular setup has proven to be the most effective in optimizing our model's performance. In terms of performance evaluation, specifically using Roche F1, F2, and L score, we have observed that the module size S2 with open field dataset outshines the other modules and surpasses the baseline model which has no embedding extensions. This indicates that OS2 delivered the most robust and effective result. This graph shows the comparisons. Now we have got our best model. Our next stages involve inferences and deployment. The inference process is a critical phase to ensure the quality and the effectiveness of model before we deploy them for real-world use. This process involves the following steps. First, we tokenize articles. After tokenization, we implement sentence splitting. Next, we use the best performing model we have fine-tuned for our specific task and data. With the generate candidate and goal summary, we may collaborate with business domain expert and conduct human evaluation to ensure our model align with real-world expectations and standard. All these steps leads to the deployment. Thank you for your time and I hope this overview provide a clear understanding of the process of the research project. Please visit my GitHub for the working code.